So the third remark that I wanted to point out to you is that you can actually integrate power series term by term as well. And to be more specific, if you have this function has a power series representation, and you know that it has radius of convergence r bigger than 0. So by the way, you're centered at z0. Your radius of convergence is r bigger than 0. And then you pick any path inside of your disk, then you can actually integrate term by term. Let's just say it this way. Then we can integrate term by term. And what does that mean? Well, it means that if you want to integrate f of z along this curve gamma, that's going to be the same thing as, well, integrating this series. And you can actually say that's the same thing as the sum, n equals 0 to infinity. Pull the cn's out of each integral over gamma z minus z naught to the n dz. And so we'll see this a little bit more later on, but I wanted to point out to you that you can differentiate power series term by term, and you can integrate these power series term by term on their disk where the function converges absolutely. All right, one more comment that I wanted to make was there's sort of this equivalence of power series and Taylor series. In the book, you would have read this, but I just wanted to highlight it again. So if your function f is analytic on this disk, when you know you're analytic on a disk, then you have a unique Taylor series expansion on that disk. So let's write that down. Then f has and it's unique, Taylor series. You could say expansion, representation, whatever. I'll say representation on our disk. And of course, you guys know what that is. It's f of z equals n equals 0 to infinity of the nth derivative of f at z naught over n factorial, and then z minus z naught to the n. So if you're analytic on this disk of radius r centered at z naught, then you have a unique Taylor series representation on that disk, and vice versa. Actually, that's the part that I'm going to talk about. So what's the vice versa? So if you have a power series, and I'm going to enable call this series g of z, right? It's a function. If it's a power series with radius of convergence r bigger than 0, so I'm centered at z naught, and it converges for some positive r bigger than 0, then this actually is then these CNs follow the Taylor series formula. This is a Taylor series. So we can say then this coefficient c to the n is just the nth derivative of g evaluated at z naught over n factorial. And we should also add, and this function g of z is analytic on the disk z minus z naught less than r. So I just want to make sure we're very, very clear here. If you are analytic, then you have a Taylor series. If you are a Taylor series that converges on this disk, if you are a power series that converges on this disk, then in fact your coefficients satisfy the Taylor series formula. So we're talking on both of these cases about some open disk centered at z naught of radius r. All right, so I wanted to end this part of the video with an example that you guys actually did in your homework. So let's think about this particular function, f of z, and let's point out that f is not analytic at z equals 0. All right, and so when it's not analytic at z equals 0, then you know that f does not have a power series representation at z equals 0. But in the homework, you guys showed that, trying to write fast here, but I want to make sure it's somewhat legible. You showed that f of z is what? 1 over z squared plus 1 over z plus 1 over 2 factorial plus z over 3 factorial plus z squared over 4 factorial plus so on and so forth. So this is what we did is we just took the series representation for e to the z and we divided by z squared and we got this. And so somehow, like, what's up with this? So I'm saying because I'm not analytic, I don't have a power series representation, and yet that kind of looks like a power series representation. And so I'd like you guys to think about for just a minute, maybe pause the video, why isn't this a power series? That's the question that we want to think about. And I'll actually answer that in the next part of the video series.